Okay, all right. So again, reminder, test corrections are due Monday, still by the end of the day. You'll have time in class to work on it. Retest in class. We're going to retest. And then today, separation of variables. Next test, last test, is this Monday. Okay, so next week we'll be doing AP classroom review, and then we'll have the test on Monday. All right, here we go. 6.4, separable differential equations. And then we're also going to talk about exponential growth and decay in this. It's all right. It's good to see you again. All right. What is a differential equation again? So if I gave you something that I said dy dx equals, what do we think of that as? Not so much just as a variable, but what is dy dx? Okay, a derivative. Okay, what I want you to still think about is that just represents slope. Okay, whatever function, my dy dx function they give me, that is the slope. Okay, that's the connection from 6.1 that we talked about yesterday. It gets into slope fields. If they give me dy dx, that is essentially my derivative function to find the slope at any point I want to put in there. All right, now we're going to expand on this and talk about separable differential equations. So a differential equation of the form dy dx equals, so that right there, that defines that it is a differential equation. We have some function f in terms of y and some function g in terms of x. Right, so there's kind of a lot going on with this. So dy dx equals f of y times g of x. So we have two equations, an equation f in terms of y and an equation g in terms of x. If we have this set up, we can separate these. So these are called separable. All right, and this is f of y times g of x. So I can separate this using algebra. I'm just going to divide the f of y from both sides and then multiply both sides by dx. And I end up with 1 over f of y dy equals g of x dx. So now again, let's think of this big picture. So we started out with dy dx. If we want to find the original function, now we have 1 over f of y dy, g of x dx. Now if we anti-differentiate each side, we'll find the initial solution, what our original equation was. Okay, because we're given a differential equation. If we want the original equation, we have to anti-differentiate. But we can't anti-differentiate a product fy gx. We have to separate it. And now conveniently it's 1 over f of y with respect to dy or times dy. So our variables are the same, so I can integrate. Okay, all right, here we go. Let's do one. Let's solve for y if they give me the differential equation dy dx equals x times y squared. And we went to solve with this initial condition when y equals 1 when x equals 1. Okay, I can recognize that this is a separable differential equation because I have two functions, x and y. And I could break this up and say, well, this is the same as x squared y squared or y squared x squared, same thing. And so I can separate this to say, well, that's the same as 1 over y squared dy equaling x squared dx. Now, question for you, don't write this down yet. Okay, so we're going to integrate each side or anti-differentiate each side. Don't write this down yet. Okay, is this right here on the left the same as my integral from y to the negative second dy? Can I do that?
Yeah.
Yes, because when I anti-differentiate, what do I end up with?
Negative y.
So I'm going to add 1 to the exponent, and so it'd be a negative 1, and I'm going to divide by negative 1, and so I end up with a negative y to the negative first. Okay, that's okay. That's allowed, which is 1 over, or negative 1 over y. Well, hold on, we'll get to that in a second. Okay, but I want you to recognize if we had 1 over y dy, what is the integral of 1 over y dy? Natural log of y. Okay, so do not get these confused. We could do this because it was y squared. We can use our negative, bring it up to the top, make it a negative exponent, and we could keep going. But if it's simply 1 over y, that is natural log of y, because if we wrote this as our integral of y to the negative first dy, add 1, we get y to the 0, and then 1 divided by 0, and that can't happen. Okay? Jacob. And this one, I think it's easiest just with exponents. Okay? All right, so if we anti-differentiate both sides, now you can start writing down again, but this is basically what I wrote down, but I want to make sure before I slid this onto the screen that we were comfortable that this does work. So now this becomes a negative 1 over y equaling the integral on the right, 1/3 x cubed plus c. So the question Zach said a second ago, well, why don't we write this as 1 over y plus c equals 1/3 x cubed plus c? Why didn't I write the plus c on the left? What do you think, Sean? Well, they don't cancel. They combine. They combine to be still a constant number. So say this was plus 7 on the left and plus 2 on the right. I would bring the 7 over. It would still be just some constant value. So that's why we don't have to write it, because it's still just some constant value.
So basically, c isn't like.
All we care about c is that we know it is a number. I don't care what number it is, but I know it's a number.
So it's not like a variable.
No, it's a number. Okay, it doesn't matter to me if it's -5 or 115. It's just a number. So all I have to do is put the c on the one side. You don't have to put it on both sides. Okay. All right. So we're not done yet, because the original problem said to solve for y. We're done with the calculus piece. Now we got to do some algebra to actually get this to simply be y equals something. Okay, and we have that y equaling 1, x equaling 1 piece that we have to worry about too. Okay, all right, so this is where we're at. Negative 1 over y equals 1/3 x cubed. Let's apply those initial conditions and actually solve for c. Okay, well, if y is 1, it's going to be a negative 1 over 1. And then x is 1, so that's 1 cubed. So we have just -1 equals 1/3 plus c. -1 subtract 1/3, or -1 subtract 3/3 would be a -4/3 is equal to C. All right, so we have our C value. So this is our, after we've done our separation of variables, applied our initial conditions, this is the equation we're at, -1/y, 1/3 x cubed minus 4/3, but we want to get it to be y equals. We don't want it to be -1/y. So we have to start doing some work here. Okay, so we have -1/y equals 1/3 x cubed minus 4/3. Okay, I would do this as 1/y, and this would be x cubed minus 4/3. I have a common denominator on the right already. I'm going to write it as one rational function on the right. Now, how can I solve this for C? Or I'm sorry, solve this for Y. Yes, but I cross multiply too. Okay, so this would be a -3 equals y times x cubed minus 4. Or it wouldn't be, it'd be -3. Okay, and so we could have -3 all over x cubed minus 4 equals y. And so that was our initial function. So if you gave me y as -3 all over x cubed minus 4, and you differentiate that, you'll end up with x times y all squared. Okay, but then this specifically satisfies also, if I put in 1 for x, put in 1 for y, it still works. Okay, so I put in 1 cubed minus 4, that gets me my -3. I got -3 over -3, that's 1. So it works. Okay, so this is separation of variables. You're going to have more practice with it in Math Excel, but this is what you have to do. You'll be given two functions, essentially, a differential with two functions on the other side of the equal sign. Separate them, anti-differentiate. They give you initial conditions. You got to solve for that C. And then there'll be some algebraic manipulation to set it up as y equals. All right, next thing we're going to talk about is law of exponential change. So a differential equation describes the change in growth or decay, depending on what it is. Okay, it's going to be some rate, some change going on. All right, getting back to the very foundational, a derivative is a change. Okay, change in y over change in x, slope. Okay, so there's some change in growth or some change in decay divided by a change in time. We're going to look at dy dt equals ky, where k is the growth constant if it's positive, or the decay constant if k is negative. And that k is a number, not a function. So this one is not, we're not going to treat this as the same separation of variables that we did on that first example. K is going to be some number, be 5y, whatever. All right, but it's that growth constant. Say if it doubles every 2 years, my k would be 2. Okay, let's apply our separation of variables. We can, even though it's a constant. Whoa. Even though it's a constant, this is kind of a proof that's going to lead into a formula that you're used to seeing. All right, so we can solve by using separation of variables. If dy dt is equal to k times y, we can use our separation of variables. Well, that's going to be 1 divided by y dy equals k dt. All right, and don't worry that k and dt are different variables, because remember, k is really just some number. So it'd be like 5 dt or something. If I were to integrate both sides, as we practiced already, the antiderivative of 1 over y is natural log, and we'll leave it as absolute value of y, because you can't take the natural log of a negative number. What's the derivative of a constant with respect to t? This would be kt. Okay, so if I was integrating, say 5, we would write it as 5t. Yep. All right, so here we go. So a natural log of y equals kt plus c. Okay, so again, we're trying to get to some sort of y equals. Okay, we want to know what the original function was going to be. So I have natural log of y. If I raise that to the power of e on both sides, then all I'm left with is absolute value of y. And then e to the kt plus c. Yeah. E, this is an exponent now. E raised to this. I raised both sides to the power of e. Okay, so if it's absolute value, well, then I know y is going to be plus or minus e to the kt plus c. Does anybody remember our exponent properties? If I have a sum in my exponent, can I separate those? Okay. How do I separate those? So this is the same. So e raised to the kt times e to the c. You can separate that. Yeah, sure. Okay. All right, this e to the c. This is e raised to some number. Okay, so I'm gonna call this a. All right, so I have y equals plus or minus e to the kt times a. So ultimately then, a is just a variable, so I'm going to say a times e to the kt, and I'm not worried about it because now e raised to the kt, that's only going to be positive. Okay, e raised to the kt, I can only get a positive number out of that. Okay, even if I had a 0 or anything, it's still going to be positive. Okay, so the law of exponential change. You have used this formula a bunch already, but this is showing how calculus will show you. So this is kind of like the continuously compounded interest formulas. A is the initial amount, e raised to the k times t, whatever k is the percentage, times t. So this is using calculus to show how this equation was derived. You'll see. Okay, all right. No more new calculus this term. We're not done for the day yet, but no more new calculus. Now we're going to do a little bit of algebra, and it's easy algebra. Okay, so this lesson, there's the separation variables, which is really important for calculus. Okay, but kind of the last third of this assignment or so is going to be dealing with algebra stuff. Okay, so the next stuff we do is nothing, it's not calculus. Okay, so you've done all the calculus for this term. There's no new calculus that you're going to have to worry about. Okay, here we go. Continuously compounded interest. Okay, this is a refresher. This is good to see again, but this will hopefully you'll be able to just fly right through this stuff. So if I want to know the amount of money in an account after T years at an annual interest rate R, and remember if they say it's 5% interest rate, our R is actually 0.05. So if they give you a percentage, make sure you convert it to a decimal, is this. So you have seen this before. The last slide, we derived how this formula came about. Okay, and again, where just that A sub 0 is that initial amount. So you're going to have some math Excel problems where you're going to use this formula, and they're going to say, okay, you start with $500, continuously compounded at 2%. How much money will you have after 10 years? Okay, so that'd be a nice problems to work on to finish out the math Excel that we're working on. Okay, but this is a formula. Make sure you have this in your notes. This is continuously compounded. So continuously means it's not monthly, it's not daily, it's continuous every second or even smaller segments in seconds. Simple compound interest. You've seen this before too. Now they will give you some K, and so they'll say if it's compounded monthly. And so if it was compounded monthly, my K would equal 12. Okay, so you'd still do the initial amount, 1 plus your rate divided by 12 if it was monthly. And then 12 times T, they'll say after 10 years, how much money will you have? All right, continuously compounded is your best bet if you're doing any investing. I don't think I've ever seen a continuously compounded offer though to invest in, but I'm sure they're out there. Yeah, if it makes sense. Okay, but credit cards, actually, take that back. Credit cards are often, I don't know if they do it continuous, but they might do it daily or something where they're charging you interest. That's why credit cards are so bad. If you get behind in credit card payments, that it goes up really fast. But to the consumer advantage, like a bank, they're not going to offer you as nice of terms. Okay, and K is the number of times compounded per year. Okay, so you're going to have some interest problems, continuously compounded, simple compound interest. All right, nothing to do with calculus, but it's in our book. We're going to go ahead and cover it. Should be pretty easy for you. Another thing they're going to talk about again is half-life. Okay, so by your enthusiasm on this, I can tell that you guys have seen it before. Time required for half of the radioactive nuclei present is sampled to decay. So this is off of that exponential formula again, but it's a negative in the exponent. So you should have it now. You got it. You got it down pat. These are, like I said, these are easy. This is a nice kind of brain break, hopefully, that it's not. So these are all formulas that we derived with calculus. So that's the connection. No. Okay. So just a reminder on that. And then let's just do a quick example of half-life. So find the half-life of a radioactive substance with the decay equation and show that half-life depends only on K. All right, so this one I kind of moved around a little bit. So whatever my initial amount is, my y sub 0 times e to the negative kt, it's going to be half of my initial amount. Yeah, do that. Yep. Yep. So again, this would be the half-life, and then this is the initial amount y sub 0 e to the negative kt. Yep. Okay. So if I wanted to make that y sub 0 e to the negative kt, I know that's going to end up being half of my original amount. So that's why it's half of y sub 0. Okay, so again, we started out with y equals y sub 0 e to the negative kt. Well, I know my answer here is going to be half of that original amount. This is the half-life equation. So half of, it'll come back. And I don't know why it does it. I'm hardwired in, but there you go. Okay, so that's all this is saying is we're still using that same formula, but we want to show that half-life depends only on K. All right, well, if I have y sub 0 equaling y sub 0, I don't have to worry about that. That's like saying 5 equals 5. So I'm only left with e to the negative kt equals 1/2. Okay, I'm trying to solve for t. All right, well, if I wanted to solve for t, I have e to the negative kt equals 1/2. I'm trying to get that t down. So if I take the natural log of both sides, then the negative kt comes down, and I have equaling natural log of 1/2. Solving for t, t is going to be equal to natural log of 1/2 divided by a negative k. All right, and let's not worry. So it depends only on k. Let's only work with a positive k. So t would be equal to 1 over negative k minus natural log of 1/2 is the same thing as saying natural log of 2 to the negative first. Well, if I'm taking natural log of 2 to the negative first, that's the same thing as a negative natural log of 2. So I have 1 over a negative k times a negative natural log of 2. If I have a negative times a negative, that becomes positive, so it becomes natural log of 2 all over k. Okay, so this is the half-life formula that you've probably seen for t, is that natural log of 2, and the k might have been a different variable, but this is how half-life is worked with as well. And then another formula that you might see would look something like this. If I'm given an initial amount, I'm going to multiply that by half, and then raise it to the exponent of t, which again represents the number of years, divided by whatever half-life they give you. So if there's a problem and they give you the half-life, let's say the half-life is 4,500 years, you can jump to this and it'd be t over 4,500, and then they're going to expand it out, say, well, what's the half-life going to be after 15 years or whatever it is. So you have, I know you have one like that in there. That's why I added that formula in as well. Okay, so after our little celebration slide, none of that stuff is calculus. It's just doing that exponential growth, decay, compound interest, half-life. That's it. You did it. 6.4, last math Excel for this term. And then next term, we are going to do 3 math Excel assignments. So we're not out of the woods yet with math Excel. But next term, we're going to do more calculus for those three sections. Then it's review time.